Now let us see what is the viscosity and some formula for the viscosity. We already see in our previous discussion that viscosity is your internal resisting force offered by one layer of fluid to the other layer of fluid if there is some relative velocity between them and when the fluid is in motion. So we know that the fluid is in motion when there is a shear stress applied on it, and if there is a shear stress applied on it, then there should be some relative velocity between different layers of fluid, and because of that one internal resisting force is acting, and that phenomenon is known as your viscosity. Now let us see that once we cover the basic concept of viscosity, let us define the viscosity mathematically. So if I say, let us suppose that this is a solid plate. This is a solid plate over which your fluid is flowing, right? And this solid plate or this solid surface is at rest at present, right? This solid plate or this solid surface is at rest. We'll make it again. This is a solid surface over which fluid is flowing and it is at rest. Let us say these are the fluid layers which are flowing over this solid surface. These are the fluid layers. The layer which is adjacent, which is in contact with this solid surface, will attain the velocity of this solid surface by the concept which we know as no slip condition. Right, there is a no slip condition exists between your solid surface and the layer of the fluid which is in contact with the solid surface. And if I say we'll take the direction of flow, I take it in the x direction, and the perpendicular to the direction of flow will take it as a y direction, right? The fluid is flowing in this direction, so in this direction of flow is the x direction and perpendicular to is the y direction. So we know that when we go above from this solid surface, when we go in this direction, the velocity is increasing, right? The velocity of this layer is 0 because the solid surface velocity is 0. As we go above, in the positive y direction when we go, the velocity is increasing. Now for our better understanding, we'll take two adjacent layers. These two layers are the adjacent layers, right? They are adjacent layers. Just for your better understanding, we take it with some distance, but they are the adjacent layers. And I am saying the distance between these two layers, is dy. The distance between these two layers is dy, and suppose if this lower layer is moving with velocity u, then this upper layer is moving with velocity u plus du. This upper layer is moving with some velocity u plus du. The velocity of this upper layer is more than the velocity of this, we know from our previous concept. So if this velocity is u, then this velocity will be this layer velocity will be u plus du. Now if I say, let us say that when t is equal to 0, when time is equal to 0, there are two fluid particles in these two layers. Suppose these are the two fluid particles. Let us say this is particle 1, this is particle 2, right? These are separated by a distance dy. This is when time t is equal to 0. When we say that after time dt, after a very small time dt, this particle will move, this particle will also move, right? This particle will move in this direction. The distance is speed into time. The velocity of this particle is u, so the distance covered by this particle in time dt is u into dt, and the distance covered by this particle in time dt is u plus du into dt. So if the velocity of this second layer is more, then the distance covered by the second, this fluid particle 2 is more than this particle 1. Hence we say that this layer, if this is vertical, then after this time dt, there will be some angular deformation in it. So if I show here, suppose this is the particle 2, suppose this is the particle 2 and this is the particle 1. This is the particle 1. Initially the distance between them is dy, and this is the case when t is equal to 0. Then after some time dt, this particle will move this distance. Let us suppose this particle 1 will reach here. We are saying, let us say that this particle 1 will reach at this point. This much distance covered by this particle 1. How much is this distance? U into dt, in time dt. And this particle 2, we say that this will cover the more distance. Let us say this particle 2 will come to this point. Suppose this is 2 dash, this is 1 dash. How much is this distance? This distance is u plus du into dt. U plus du into dt. So after time dt, the angular deformation, we say that now this is the angular deformation. Initially the fluid particles are this much in this vertical line, right? Initially the fluid particles are like this, and after time dt, they will angularly, there is some deformation in that because of this relative velocity, because the velocity of this upper layer is more than the lower layer. So there is some angular deformation, and I say that this angular deformation I represent it with angle d theta for time dt. As time is increasing, then this angular deformation will continuously increasing, right? And so hence we say that the angular deformation in the case of fluid, when it is subjected to a shear force, is a function of time. That is not in the case of solid. In the case of solid, that angular deformation or the shear strain is constant, right? Is constant. But in this fluid case, the shear angle or this shear deformation or this angular deformation is a function of time. So this distance is, how much is this distance? This is dy. How much is this distance? This complete is u plus du into dt. This is u into dt. So this is also u into dt. So how much is left? Du into dt. Du into dt. So from this right angle triangle, I can write tangent d theta is equal to, tangent d theta is du into dt divided by adjacent side, that is dy, right? Du into dt divided by dy. And for small angle, we know that for small d theta, you can write tangent d theta is approximately equal to d theta. We know that if the angle is small, sin theta को आप लिख सकते हैं theta. If angle is small, cos theta is 1 and tangent theta is theta. If the angle is small, we know this, right? So I can write tangent d theta is equal to d theta. So from here we get d theta is equal to du into dt divided by dy. And if you rearrange it, you will get d theta by dt is equal to du upon dy. D theta by dt is equal to du upon dy. This is the important relation of your fluid mechanics, that d theta by dt is equal to du upon dy. What is this d theta upon dt? This is rate of angular deformation with respect to time. So d theta by dt is rate of angular deformation or shear strain, rate of angular deformation or shear strain with respect to time, with respect to time. And what is this du by dy? Du by dy is the change of velocity with respect to distance y in the direction perpendicular to the direction of flow. The fluid is flowing in the x direction. We are taking the velocity gradient in the direction y. Y is the direction perpendicular to the direction of flow. So du by dy is velocity gradient. Gradient, if somewhere you heard the word gradient, gradient means with respect to distance, and this rate, always rate means with respect to time and gradient means with respect to distance. So du by dy is velocity gradient in the direction perpendicular to the direction of flow. Perpendicular to the direction of flow. We are saying this. So in fluid mechanics we say that the rate of shear angle or the rate of shear deformation is equal to the velocity gradient in the direction perpendicular to the direction of flow, that is du by dy. And we assume that in this case we assume that there may be the case that velocity gradient is present in the direction of flow also, right? Du by dx is also there. We take that. But in this we assume, in this derivation we assume that there is no velocity gradient in the direction of flow, right? Means if on this layer each and every particle, on this layer each and every fluid particle is moving with velocity u, right? It is a uniform flow. We are taking it is a uniform flow. So we are saying that we are not taking into account the velocity gradient in the direction of flow. We assume that it is a uniform flow, right? This is the assumption here. Assumption will be your uniform flow. You are taking assumption as uniform flow, and we will discuss what is a uniform flow in our fluid kinematics chapter. We will discuss it. Assumption will be uniform flow. That means we neglect the velocity gradient. We neglect the velocity gradient in the direction of flow. You neglect it, right? So d theta by dt is equal to du by dy, right? So this is the one formula, d theta by dt is equal to du by dy. You have to remember this. We will use it in our in our later discussions also. This formula is most important, that the rate of angular deformation is equal to the velocity gradient in the direction perpendicular to the direction of flow.